Hello, my name is Talia. I'm a high school senior and I love teaching others about chemistry. This YouTube channel is an extra resource for anyone who may be needing some help in their chemistry classes. This week, I'm going to be doing part 2 of my gas law video series, and I'm going to be talking about Gay-Lussac's law as well as the combined gas law. If you need help with either of those gas laws, feel free to keep on watching. Without further ado, let's get started. Okay, so with Charles's law and Boyles's law, they each kept one component of the pressure, volume, temperature relationship constant and compared the other two. With Gay-Lussac's law, volume is kept constant and pressure and temperature are compared. So Gay-Lussac's law is P1 over T1 is going to equal P2 over T2. Staying consistent with the rest of our units in these past gas laws, initial pressure is represented as P1, initial temperature is T1, final pressure is P2, and final temperature is T2. Just like Charles's law, the only constraint on units is that temperatures must always be in Kelvin. So the relationship that this law shows is that when temperature is increased, pressure is increased, which makes sense because when you increase the temperature and keep the volume of a container constant, the molecules will move faster and they'll spread apart. So more force will be exerted in the area. And the opposite is also true. So as I mentioned briefly in the past video, this is a direct relationship because as one variable increases, the other one does as well. Just as a reminder, an inverse relationship is when as one variable increases, the other variable decreases, which can be seen in Boyles's law. So now let's do some practice with Gay-Lussac's law. So a sample of gas has a pressure of 5 atmospheres and a temperature of 50 degrees Celsius. What will be the pressure if the temperature is increased to 230 degrees Celsius? So if temperature is increased and volume is kept constant, we know we are also going to have an increase in pressure. So let's label the variables that we have. We have our initial pressure and we have our initial temperature. We need to convert it. We're looking for our final pressure and we have our final temperature. So let's first convert our temperatures. So if we add 273 to 50, we have 323 Kelvin. If we do 230 plus 273, we get 503 Kelvin. And remember, to get from Celsius to Kelvin, you just add 273. So now let's write out our equation, and then we can write out what we have. 5 atmospheres over 323 Kelvin is equal to the pressure that we are trying to find, the final pressure, over 503 Kelvin. And to get rid of the 503 in the denominator so that we can isolate final pressure, I'm just going to multiply both sides by 503 Kelvin, and so it will cancel out on the right. And then I am just going to plug all this into my calculator. So 5 divided by 323 times 503. So our final pressure is going to be 7.8 atmospheres. Now let's do another practice problem. So a sample of argon has a pressure of 7.60 times 10 to the 4th pascals at 200 Kelvin. What will be the pressure at 700 Kelvin? We are going to increase temperature, which means we are going to increase pressure as well. So we have our initial pressure, initial temperature. We are looking for our final pressure and we have our final temperature. And our temperatures are already converted. So let's write out initial pressure over initial temperature equals final pressure over final temperature. So we have 7.60 times 10 to the 4th pascals over 200 Kelvin equals our final pressure over 700 Kelvin. So again, we can multiply both sides by 700 Kelvin, and it will cancel out on the side with final pressure. And then we just plug into our calculators 7.6 times 10 to the 4th divided by 200 times 700. And we get 2.66 times 10 to the 1, 2, 3, 4, 5 pascals as our final pressure. And we know that the units are going to be pascals because we have Kelvin here and Kelvin here. So these units are going to cancel out and all we have left are pascals. And that is why in all of these gas laws, you can use different pressure or volume units as long as they're consistent because they will cancel out. The only constraint is that the temperature always has to be in Kelvin. Now we are going to move on to the combined gas law, which just relates pressure, volume, and temperature with nothing being held constant. So we have P1 V1 over T1 equals P2 V2 over T2. And if you look, this is literally a combination of Boyle's law, Charles' law, and Gay-Lussac's law. We have Boyle's law up here, we have Charles's law here, and we have Gay-Lussac's law over here. Just like in our past three laws, P1, V1, and T1 are all initial pressure, initial volume, and initial temperature. P2, V2, T2 are all the final pressure, volume, and temperatures. And again, the only constraint is that the temperature must always be in Kelvin. So let's do some practice. 200 liters of gas in a flexible walled container is prepared at 700 millimeters mercury and 200 degrees Celsius. The gas is placed into a tank under high pressure. When the tank cools to 40 degrees Celsius, the pressure of the gas is 30 atmospheres. What is the volume? So let's go through and see what we have. We have our initial volume, and we have our initial pressure, and we have our initial temperature, though it will need to be converted. Our final temperature is here. We have our final pressure, and we are looking for final volume. Step one done. Now let's convert our temperatures. If we have 200 plus 273, we get 473 Kelvin. And if we have 40 plus 273, we have 313 Kelvin. So the past relationships that I talked about in Boyle's law, Charles' law, and Gay-Lussac's law are not exactly the same in the combined gas law because in those situations, something was held constant. Here, nothing is held constant. So now we've converted our temperatures, and if you notice, we do not have a consistency in our pressure units. So we need to convert our atmospheres to millimeters of mercury. So we're going to quickly do that conversion. So we have 30 atmospheres times 760 millimeters of mercury over 1 atmosphere, and that is going to be 2.28 times 10 to the 4th millimeters of mercury. Okay, so now everything is consistent. So now let's set up our equation. I'm just going to write it out. So now let's plug in what we know. Our initial pressure is 700 millimeters of mercury. Our initial volume is 200 liters. And that is going to be over 473 Kelvin. And that is going to equal our final pressure, which is 2.28 times 10 to the 4th millimeters of mercury. We are looking for the final volume all over our final temperature of 313 Kelvin. So now we need to isolate the volume. So what I'm going to do is bring this to the side. So if we multiply both sides by 313, that will cancel out our denominator on this fraction. And then we would have to also divide both sides by 2.28 times 10 to the 4th millimeters of mercury. And that will cancel this out. So I'm going to write that on the denominator here. So now we have kind of a huge fraction that we need to plug into our calculator. With this, it's really important that you put parentheses around the denominator because otherwise it will divide everything and then multiply by 473, and that's not what you want. So I'm going to do 313 times 700 times 200, divided by 2.28 times 10 to the 4th times 473. And I get 4.06 liters. So that is the final volume. So next, what is the volume of a gas at 3 atmospheres and 200 Kelvin if its original volume was 300 liters at 0.25 atmospheres and 400 Kelvin? This question is kind of tricky because the original comes after the final. So we are looking for the final volume. We have our final pressure. We have our final temperature. We have our initial volume, our initial pressure, and our initial temperature. So now let's write out the combined gas law. P1 V1 over T1 equals P2 V2 over T2. And let's substitute what we have. Okay, I'm going to do the initial first. I have 0.250 atmospheres times 300 liters over the temperature of 400 Kelvin. And that equals 3 atmospheres times V2 over 200 Kelvin. So now we're going to do the same thing. We're going to multiply by what's on the denominator, which is 200 Kelvin. And I'm going to multiply it here. And then we are going to divide both sides by 3 atmospheres. And that is going to cancel out the 3 atmospheres on the side with the volume. And I'm going to put that. I'm going to also divide by 3 atmospheres on this side. And once again, remember that the denominator needs to be in parentheses in order to have proper order of operations. So I multiplied by the denominator and divided by the numerator on both sides. So now I'm going to do 200 times 0.25 times 300 divided by, and I'm remembering to put in parentheses, 3 times 400. So if I plug everything into my calculator, making sure to put parentheses around the denominator, I get that our final volume is equal to 12.5 liters. And that is our practice on the combined gas law. So that was this week's video. Next week, I'm going to be talking about Avogadro's law and the ideal gas law. So I hope you'll join me back next week if you need some extra practice with those topics. As always, feel free to leave me any questions or comments or any confusion you might have in the comments, and I will do my best to answer your questions. I hope you enjoyed this video, and good luck with learning the rest of your chemistry.